got a question here also from the homework assignment number 15, number 5. This is question 14. And it's gobbledygook, right? So let's begin by just reading the question. So let me go to red here. Consider a 1 mole of monatomic ideal gas. All right, so let me make some notes out to the side. N is equal to 1 mole, okay? 1 mole of a monatomic ideal gas that undergoes a reversible isothermic, okay, there you go, expansion at temperature 310, okay, and V1 is equal to 0.5 liters and V2 is equal to 1.8 liters, okay? So calculate the magnitude. All right. So we got lots of things we got to worry about here. Calculate the magnitude of work, heat, change in internal energy, change in enthalpy, and change in entropy for this process. All right. So first of all, let's just start with work. We know that work in an isothermal expansion, work is equal to nRT, natural log of V2 over V1. And we got this equation off the front of our exam, right? So this is not an equation that I think I'm asking you to memorize, but you do need to know when you can use it. You use this with an isothermal expansion. So if this is true, well, we know all of these. Okay, we have to look up work. We have to look up R. R is 8.314, 8.316, I don't remember. 8.314 or 8.316. Gas constant is equal to 8.314. Yep, 8.314. Okay. So let's go back over here. 8.314 joules per mole Kelvin. And I want to use joules per mole Kelvin because this is moles. I want work in joules, right? So that's why I need to do that. So now that I got that, I can say work is equal to 1. And I work to get my units all in the right I work to get all my measures in the right units, moles, kelvins, in joules, so I don't have to worry about this. 8.314 R, that's R. T is 310, right? And the natural log of V2 is 1.8 over 0.5. So this is going to be, my work is going to equal to 8.314 times 310 times natural log of 1.8 over 0.5. And that is 3301. Okay, 3301. 3301. Not to worry about, let's just calculate the magnitude. So frankly, the way the question's written, it ought to be simply 3301. But I think that the way the question's set up, we are gonna if this is on the exam, we're going to leave it as magnitude, right? So 3301 would be good enough. But is the gas done for this process? So is the process being done on the environment, or is the work being done on the gas itself? And the work is being done on the environment, right? So we're going to say negative 3301 because it's leaving the system, okay? Negative 3301 joules, right? Now, we also know that Q, for an isothermal process, we know, let's go to a different color here. We know that that is equal to Q plus W, but for an isothermal process is equal to 0, right? And so Q is equal to a negative W, and so Q is equal to positive 3301 joules. That's the change in heat. Okay? So we took care of those first two. Looks like we're ready for the next one too. Delta U, the change in internal energy for an isothermal process is 0, so we don't have any calculations to do there, right? Let's go back to green for delta H. Delta H, recall, is defined as the delta U plus PV, which is equal to delta U plus the work, right? Which is equal to 0, because delta U is 0, right? Plus the work, which is minus 3301 joules. And so delta the change in enthalpy is minus 3301 joules. All right, and then finally, the change in entropy. And this comes from chapter 20. The change in entropy of an isothermal process is like it's NR natural log, or NR, yeah, natural log of V2 over V1, which we didn't, we're not going to worry about why that's what it is. This is on the front of your exam. And so this looks exactly like changing, this looks exactly like work, doesn't it? There you go. Look at that over there. It looks like the same as work. In the work, except it's got the factor of T in it. So this looks like this is nRT over ln V2 over V1 divided by T, right? You see how those just cross off and it becomes that. So this looks like it's going to be 3301 divided by 310 kelvins, right? Which is equal to 3301 divided by 310 kelvins is equal to 10.6. 10.6 and the joules per Kelvin. And the final thing I have to worry about is this positive or negative, right? Is this becoming more ordered or less ordered? It's definitely becoming less ordered. So the change in entropy, is going to be positive, right? Because it's becoming more disordered, where entropy is degree of disorder, it's getting more disordered, and so it's 10.6, positive 10.6, all right? So here's the first question, work. There's the second question, heat. There's the second question, internal energy, enthalpy, and entropy. All right, hope that's helpful.